In this video, we will introduce the idea of lattice energy and use it in conjunction with Coulombs Law to predict the lattice energy of ionic compounds. So lattice energy is a way of explaining the concept that ionic charges have to have energy put in to pull them apart. So picture, for instance, sodium chloride, Na plus combining with Cl minus. So these ions are held together strongly by the opposite charges. And to pull them apart, I have to put energy into that. And in order for them to, when they go back together again, it would be the opposite, right? So energy gets released. So if energy gets put in to pull them apart, endothermic process, energy is going to be taken out to put them back together. All right, so that's a general idea there. So let's consider a problem here. So consider the formation of NaCl. What is the energy change for the following? So we're going to look up the energy change in each of these, or the enthalpy. So when Na forms sodium ion, this could be called the ionization energy. So the energy it takes to remove the first electron, the first ionization energy, and in this book here, we have 496 kilojoules per mole. So we could call this value here 496 kilojoules per mole. Okay, and that's a positive value. So it is putting energy in. So it takes, you have to put energy in order for the electron to be removed. All right, well, let's consider this one here. So we can also look up the value for the addition of an electron to the chlorine, and that one is called the electron affinity. So the energy change when an electron gets added to the chlorine, and so that's negative 349 kilojoules per mole. All right, so this one would be negative 349 kilojoules per mole. So looking at that, if you do the math on it, we would find that the overall enthalpy is going to be a positive value. So if we did 496 minus 349, you're going to get positive 1. So the overall here is positive 147 kilojoules per mole. So in other words, it's endothermic, energy is being put in, but we know that the energy change in which sodium chloride is formed, the enthalpy of that is exothermic. So how do we explain this? Well, let's consider another point here. So just like we just mentioned here, these two reactions, they only provide the energy it takes to remove the electron from the sodium and to add an electron to the chlorine. So in other words, they don't discuss the energy change involved when the ions themselves come together. So that itself is another energy change that needs to be considered in this picture. So if we look at this in a more complete way, we're going to have to put that picture in. You see, if we added together these two reactions as it is, the sodium combined here with and the chloride forming. So these two reactions alone do not add up to sodium chloride. So now we've got to show, and these would be in their gaseous forms, gaseous, solid, this would be gaseous as well. So now we need to show how these ions come together. So sodium plus chloride combines to make sodium chloride. So in this process, notice that we've got to put another step into this. So here's our enthalpy here, 496 kilojoules per mole. And then we have negative 349 kilojoules per mole. And this value, we could look that one up. And so that value, the lattice energy value for this is right here. So the value it takes to separate is positive 788 kilojoules per mole. So if we reverse the process and showed the energy involved to put together the sodium and chloride, it'd be negative 788 kilojoules per mole. Alright, so now let's try adding those together using Hess's law and see what we get. So if we put all of these together, the sodium ion crosses here. The electrons are on the products and reactant side. The chloride ion is on the product and the reactant side. And so our overall or net reaction looks like this. Sodium plus the chloride produces sodium chloride. Add together these energies and we get the value negative 620 kilojoules per mole. And so we see that this is in fact exothermic if you consider the complete reaction that also takes into account the fact that we have ions that then come together, and that is a process that releases energy. So lattice energy is a way of describing the energy it takes to separate a mole of an ionic compound into its gaseous ions. Sodium chloride, for instance, forms in this network grid structure. So the ions would naturally arrange themselves so that the positive is next to the negative, and so on. So you get this sort of grid-like structure forming. So the lattice energy tells us how much energy it takes to pull apart the positive from the negative. And again, we can use that in reverse as well if we want to know how much energy is released when they are joined together. So we see here that this one was negative 620 kilojoules per mole in the case of the sodium chloride. So let's take this in conjunction with Coulombs Law to make some predictions. So Coulombs Law states that the attractive force between any charges or ions is directly proportional to the charge and inversely proportional to the distance. If you look at the equation here, you can think of that in terms of some simple math. So let's say we had a simple fraction here, like 1 over, and then let's say I have this one over 4. Now, when the number on the bottom increases, we see that there's a change with the overall value. So 1 over 2 is 0.5, 1 over 4 is 0.25. So the number is getting smaller. Therefore, we see here that for the distance, the larger that number gets, the smaller the force gets between the two charges. So here's one charge. Maybe this is the positive charge. Here's maybe the negative charge. So the larger the distance is between them, the smaller the force is. All right, well, likewise, thinking about these simple numbers again, if I had 1 over 2, and then I had 2 over 2, 1 over 2 becomes 0.5, 2 over 2 becomes a number 1. So we see that as any number on top gets larger, the overall value increases. So Q, this represents the magnitude of the charge for charge 1. This Q2 would be the charge of charge 2. And so as that magnitude increases, we see that the overall force would increase as well. And then K just represents a constant. So thinking about Coulomb's law in a qualitative sense, it is kind of a common sense sort of thing. If the charges are further away, the forces are smaller. Okay, so the further I pull these magnets apart, the weaker their force gets. So when they're really far apart, there's very little force in between them. But as they start to get closer, I've got to actually put a little force into these to keep them from coming together. And then when they get really close, it's almost impossible to keep these things apart. So the closer they get, the stronger the force. Now likewise, if I had several magnets stacked together, if I had a stronger charge, that would also increase the amount of force as well. So that would be a direct relationship there. All right, so let's use this to make some predictions. So let's say I'm looking at a couple of examples here. I have lithium fluoride. So lithium fluoride, we have Li plus F minus. Those two combine to make the compound lithium fluoride. Now, if we think about ionic sizes, here we have an illustration. Cations become smaller than the atoms from which they formed, while anions become larger than the atoms from which they formed. So they have essentially a lower effective nuclear charge on those electrons. Those electrons spread out because of that. There's more electrons and the same number of protons. Whereas with the cations, those electrons are fewer and they get pulled in closer. And there can also be fewer energy levels. So think about the distances involved here between the lithium and fluoride. Let's go ahead and do a little sketch of that. So this one would be kind of like a circle this big, your lithium, and then here's the fluoride, kind of like a circle this big. Okay, so we're considering the distance between those. I'll call that R to correspond with our Coulombs law. All right, now let's consider the other compound here. So the other one is sodium chloride. So sodium chloride, and so those combine to make NaCl. And so if we consider the sizes here of the ions, here we have sodium, here I have chloride. And we can see that the chloride is quite a bit larger than the fluoride, and the sodium's a little bit larger than the lithium ion as well. So let's go ahead and sketch those out. So here we have the sodium. Put that there. So sodium's a little bit larger than the lithium ion, and the chloride ion is quite a bit larger than the fluoride ion. And so let's consider now the distance between those. Use blue here. All right, so we can see then that the distance in this case is larger than the distance in this case. So we'll call this one R2 and this one R1. So R2 is greater than R1. So using Coulombs law, the distance is greater, therefore the force is smaller. And so when these things are separated, all right, so the force involved in separating lithium and fluoride is greater. Now force translates into energy, right? So force over a distance, energy, is force multiplied by the distance involved. So as the force is greater and that moves apart a certain distance, the energy would likewise be greater as well. So we're going to have greater energy involved in separating the lithium and the fluoride than we would have separating the sodium and the chloride. So this would work in a similar way for the second example. We have the magnesium oxide. So the magnesium ion, we could see right here, the oxygen ion is right there. So consider the relative sizes of those and the sodium fluoride. So the sodium is right here, fluoride is very small. So if you added together the numbers here, you would find that the total distance here with the magnesium oxide is smaller than the total distance with the sodium fluoride. And so that's why we can use Coulombs law to predict that magnesium oxide would have a greater lattice energy. It has a smaller distance between the two charges.